Okay, good morning everyone. Thank you very much to the organizers for this invitation to give this talk. What I'm going to talk about today is of course modern physics given the session, but also hopefully a little bit of a different take on this. And as my title suggests, it's deconstructing modern physics with model ladders. Let me start with the big picture, and I knew that given the session, there will be experts in the session, and in particular because Rajdeep was opening the session, I knew he would give an excellent introduction. So I'm not going to bore you much with what this is, except just one slide on it. We all know that this is essentially the field. The simplest Moiré material is if you take two layers of graphene and rotate it, you have these beautiful Moiré patterns. And this twisted bilayer graphene has quasi-flat bands in the low energy sector. And the best part is the two cornerstones of condensed matter physics, they join together and their interplay give rise to a fantastic plethora of observables, right? Which is strong interaction and topology. And that's what's behind the exotic phases and various kinds of observables. These are the earlier works, and of course, these are the two pioneering experiments from the MIT group, the correlated insulators at commensurate filling, and the observation of superconductivity at slightly away from those fillings. And then finally, this was, I think, from Goldhaber-Gordon's group, the first observation of anomalous Hall effect. As you can see, there is a nice hysteresis in the Hall data. Of course, this list is now so long that I think this is the only problem ChatGPT will not be able to give you if you want a summary in the last 8 years, the way this has progressed. Okay, so that was all I wanted to tell you. Now the point is, if you follow the field the way it has traversed over the last 8 years, there's a lot of good things and a few bad things, and so far probably not too much ugly things. The first thing is the phase diagram is very rich. Okay? We all know about that. As Rajdeep was saying, practically all superconducting order parameters under the sun have been proposed and probably will come up with some more. So there is a very rich phase diagram, but the point is these are very sensitive to details. Okay? And the prevailing approach in the field, again, this is a very broad brush stroke. Some might take offense, but this is a mean field slide, okay? So the prevailing approach is you make increasingly realistic single particle models, and then you put interaction, and then you want to study what phases come out, and then you want to compare them with experiments. This is what we are doing. So you start first with the Spitzer-McDonald model, then you put strength, then you put inhomogeneity, then you put another layer, and it goes and proliferates, right? Which is good, because it also shows how rich the field is. Experimental control is there, and you can do it. But the point is, the physics, therefore, is very specific to the model and the model platform. Okay? That's how things have been progressing. Now, my point is, in this physics, as rich as it is, there are a lot of ingredients. For example, there is Dirac physics, there is sublattice, there is Rayleigh, there is spin, and so on and so forth. I want to take a slightly different path, and I want to ask the question, can I distill and separate out which ingredients give rise to which features? Okay? Or in other words, can I sort of shortlist what is universal in this and what are microscopic details that will change as you go around? Now, as you understand, this is a very big goal. And by the nature of the question I'm posing, I won't be able to answer most questions. But hopefully at the end of the talk, you will get some inkling as to what are the minimum things that might be at play, which is probably common in many platforms and giving rise to much of the interesting physics. And to achieve this goal, the point is, as we all theorists do, let us build the simplest model that, in my opinion, can capture the Moiré physics. And I'm going to study that. And I'm going to study both the band structure, the interaction effect, and finally the topology, and see what comes out. All right, here is the model. A priori, it's a 1D model. And if I just showed you this, you would think there is nothing. How can this be Moiré physics? It's just a 1D ladder. So let me tell you why I think this has the necessary ingredients for our problem. So what is this model? The model is essentially a two-leg ladder. Okay, so that's my two-ladder legs. And then I have a interleg hopping term. Now this hopping term is modulated periodically. Okay? That's our Moiré introduction. Okay? So there is some overall gamma naught constant, and there is some simplest hopping term, cosine modulated, and the hopping, the lattice constant, the new lattice constant Moiré is, let's say, capital J, and the small j is my site index, right? So gamma 1, then gamma 2, gamma 3, and then after some periodicity, again it becomes gamma j, and then again starts gamma 1, gamma 2, gamma 3. Okay? On top of that, I also have a flux, a constant flux piercing through each placket, and that is this complex part here. This capital gamma is nothing but 0 and 1, because as you will see, I want to switch on and off the flux. So it's just a control parameter, there is no meaning to it. This is the flux. Now note what I have done is, I have kept the flux per placket, it has the same periodicity J as the interleg modulation. Okay? In general, you can make a much more general model with that and them having the flux and the interleg having different periodicity, but I am interested in Moiré, and you will see this is the pertinent model to do. Okay? Now, as I said, why would I accept this? So let's first try to understand qualitatively what should emerge out of this model. See, when I have, suppose I have no flux, I only have the periodic interleg modulation. So essentially, then I have 2 degrees of freedom, 2 single chains, my cosine band dispersion, and I am adding some interleg modulated hopping. So then what will happen is, first, this is doubly degenerate, and let's say there is no interleg hopping. I apply a constant interleg hopping, then these doubly degenerate bands will just split up, standard, the 2 legs. And now, if I apply my G is nothing but the strength of my periodic modulation, then this is essentially our solid state 101, nearly free electron model. It is going to open up sub-mini bands because of Bragg scattering. So that's essentially our mini bands coming from some periodic modulation. Now, if I have the flux, what is going to happen? Again, I have 2 ladders with 2 degrees of freedom. The flux, the moment I add flux, immediately the 2 degrees of freedom will split in the momentum direction first, as we know always happens. Now I turn on the constant part of the interleg hopping. So now they will hybridize, and of course they will move in the energy axis. But you see, these 2 bands are now a superposition of the original 2 bands, because this part arises from both the bands, and so is this part. And again, you turn on the interleg modulation, again, you will have the mini bands. Okay. Now let's take, why is this very similar to TBG? So if you take twisted biallography, this is the easiest cartoon you can get, right? So I have the hexagonal Brunon zone for the 2 layers rotated, and because of the rotation, of course, the Dirac points are going to shift by some vector delta k, which means that if I'm in the low energy sector, I have Dirac cones at each Dirac point from the 2 layers, which are first shifted by this delta k. And then, because of the interlayer hopping, which is also modulated, these will hybridize, open up a gap, and finally, because of the mini band formation, because you have a larger superlattice constant, it will cut out and give you a small mini band there. So you can see the qualitative similarity here, what is happening. This momentum separation is essentially the momentum separation coming from the flux in the model, in the 1D case, and then the Moiré miniband formation is essentially coming from the interleg modulated hopping. That's the similarity here. So all I've done is I have removed all of Dirac physics, everything graphene, 2D, all gone, no sublattice, simple 2 chains, which end up giving a low energy band structure with the similar characteristics. And note that in the entire process, I'm going to be interested only in the low energy bands. So these, the lowest band in these 2 cases is equivalent to my low energy band in GEG there. So what do we gain by doing this? The first thing is, as I commented, Moiré physics will be disentangled from graphene physics. Instead of 2D Dirac, I simply have 1D parabolic. Okay. The most important thing that I'll be able to do with this is I can independently study the momentum separation from periodic modulation. What do I mean by this? you see here, there is only one scale which separates out this momentum separation, and it is that same scale 1 over delta k which is giving the periodic modulation. So the moment you twist two layers, the Moiré pattern, or rather the band structure, inherits that momentum separation together with the miniband formation. Because there is only one parameter, the angle, you cannot separate them out. And as you will see, that separation will be very meaningful soon. Okay? So I can do that here because I can turn on and off flux while keeping the periodic modulation in my study. As far as theoretical things are concerned, I can, because it's a 1D model, I can do much more controlled mini-body calculation. So I can do DMRG, and I can also do bosonization, okay, which is harder to do. Mostly we go to Hartree-Fock in the 2D case. And finally, leaving out all of this as a 1D analog, the model is of intrinsic interest. You can always, if not in a material, at least in cold latent systems, one can study these things. Okay. All right, let's come to the band structure. First, how much time?
15 minutes.
Left. Oh, okay, I'm going very slow, so let me speed up. So the band structure is, first with no flux, it's simple. So I've taken some random number, j equals 6, the periodicity. So from the two leg ladders, you have 12 bands. As I said, I'm interested in the low energy band, so this is the blow up. And these are for two parameters I'm showing you. And if you take the band width and the band gap, I mean, you get a curve. I mean, depending on the modulation strength and the overall constant strength of the interleg hopping, you will get some bandwidth versus band gap. Fair enough. It's okay. But the important point is, in the no flux case, if you take half filling of the lowest band, the number of Fermi points is always going to be 2. That will never change. If you compare that with the case where you do have flux, what will happen is, again, you will get the lowest two bands something like this, and progressively by changing the parameters, the lower band will become quasi-flat. And it has a slightly more non-trivial band gap, bandwidth dependence on parameters, not important. But the important part is, because of the band structure, now you see at an intermediate parameter regime where you have a quasi-flat band, the number of Fermi points when you cut it at half filling can have 4 Fermi points as opposed to 2 Fermi points as it cuts. Okay, let's put on interaction. Simplest form, let's put Hubbard interaction on site, and let's try to understand the half filling of the lowest band. As I said, Fermi level is here, and I'm going to do both things. First run DMRG, and then try to also do a little bit of bosonization. So let me show you the DMRG results first. So if you run it, two interesting things come out immediately. So the first thing is, if you do the charge gap versus U at half filling, you see that of course a gap opens up. There's a metal insulator transition, as we do expect at half filling. But the interesting part is the metal insulator transition is a finite U Mach transition. Okay. Why is this interesting? Because we know that in standard 1D Hubbard models, this transition is infinitesimal linear. The moment you put some U, it should open up. So that's already something which is different. Okay? By the way, this is with full flux model. Everything is intact inside. Now let's go to, so I'm showing you, we are at a parameter point here where the bandwidth is the minimum, and this is what we get. And if you go to the spin-spin correlation, there also something interesting shows up. When the band is quasi-flat and the interaction is strong, that is, the effective interaction is of the order of bandwidth, you see the spin-spin correlation is ferromagnetic. And as you increase the bandwidth, that ferromagnetic switches and becomes essentially antiferromagnetic. So again, you can see that, again, this is different from the standard 1D Hubbard model. Standard 1D Hubbard is at half filling, I should get an antiferromagnetic insulator. Okay. All right. So let's try to see what we can get. Firstly, the metal insulator part. So in recent work, we tried to do some bosonization, and we could figure out why this is happening, and this has to do with the number of Fermi points. So when there is no flux, so the figure I showed you was actually somewhere here. At that point, we weren't aware that we were doing that. We were actually dictated by quasi-flat band. But unknowingly, we actually entered the regime where the quasi-flat band had 4 Fermi points. And if you do bosonization, then in this particular point, you can show that the phase diagram becomes like this. The symbols are the standard nomenclature you use in 1D. So C is the charge sectors, S is the spin sector, and the number tells you how many ungapped modes are there. So C1, S1, C0, S1. So this means this here is a gapped out charge part, whereas this is metallic. Yeah, and this is of course gapped out everywhere. So the part where you have 4 Fermi points, it does take a finite U to open up that charge gap. But if you're in the 2 Fermi point, then you do immediately open up the Mott gap. Okay? And this will never show up if there is no flux. It will always be the standard physics because there are no 4 Fermi points to be available. Doesn't matter how low the bandwidth goes. Okay? For the ferromagnetism, life is not so easy. Bosonization does not give us anything, and for good reasons, because where FM kicks in is essentially the effective U is of the order of bandwidth, and even more sometimes. So that doesn't help, and we actually don't know where it is coming from, although we have some inklings. But we ran some diagnostics, and a couple of diagnostics are first, this is a very robust phase because this does not depend on the number of Fermi points. So if you run for a 4 Fermi parameter versus 2 Fermi, you see the very similar physics at high interaction. There is ferromagnetism, which becomes antiferromagnet as the interaction, effective interaction goes down. And this is the same story for both. So it does not depend on the Fermi points. And finally, it's a very interesting phase because it requires both flux and periodic interleg hopping. So in the first case, I have removed flux and kept only periodic interleg hopping. Doesn't matter how high you go, this is absurd, but still I'm showing you, it does not give you, it's standard antiferromagnetic. You switch off the interleg hopping and you just keep flux, because you might think it's coming from there. Right? By the way, when I keep on saying flux, there is no Zeeman coupling. Huh? This is interaction driven. Again, it's standard antiferromagnetic. So to have this phase, you really need both the flux and the interleg periodic modulation, and only then you get the phase. And finally, we tried this at other fillings. So this is what I had shown you earlier at half filling. These numbers are showing you how small the filling is compared to the lattice because I'm at half filling of the lowest band. So here I have written. So half filling is this. So this is essentially antiferro to ferro. If you go slightly below and above, so 2 particles more than half and less than half, you see the ferromagnetism, ferro is red, it persists. And the transition point hardly changes. But if you go above half filling, the ferromagnetism is there, but there is a huge asymmetry in the transition point. So the transition is happening increasingly at large. In fact, by the time you go to 3/4 filling, the transition point essentially takes 2 bands when it is already outside the band, the lowest band. Okay, so so the gist of the interaction part is, if you take only periodic interleg hopping and if you make mini bands, doesn't matter how strong interaction you put in this model, it is usual 1D Hubbard physics, which is 0 U metal insulator transition and antiferromagnetism. But if you do put both flux and periodic interleg hopping, then new aspects come out. First is this finite U Mott transition, and the second fact is there is FM phase at strong coupling. The origin of ferromagnetism remains unknown. I have had a long suspicion that this comes from quantum geometry for last 4 years, but we have not worked out a theory yet. But recent paper from Bernevik actually has worked out a theory which points to this, that in such systems, quantum geometry does give rise to ferromagnetism in otherwise innocuous models. Okay? But the take-home message that I want to take from this interaction part is, momentum separation between the contributing degrees of freedom is a crucial ingredient in Moiré physics, because that is what I am capturing through that flux. And without it, just miniband formation and making strong interaction alone doesn't give something very exciting. Sorry. Okay, in 5 minutes, let's maybe quickly give you a summary of topology. More details will be given by my student in another talk. So I have a parent Hamiltonian before I introduce any Moiré hopping or any flux. So without flux, I have the 2 bands. With flux, I have a little bit of different kind, but again 2 bands. And the interesting part is these two bands are completely trivial. If you do the symmetry, these are both A1 symmetry, and topologically in 1D, this is trivial. It cannot have topology. Now the question I'm asking is, now I turn on these interleg periodic modulation. Can that alone give rise to topology? The good part about this is, see, in twisted bilayer graphene as individual degrees of freedom already has the ingredients. It has very curvature hotspots. So there it's a lot of things going on. Here I know nothing is there to begin with. So if something comes out, I can claim that it is coming out purely from the modulation. So again, you have to look at the symmetries because this is a multi-band problem and I'm only looking at some random low energy band. Your standard 10-fold classification is not going to work. You want some other symmetry to guide you, and thankfully in our model we have inversion, which has made our life easier. There are some intricacies here which I am brushing under the carpet. Hopefully Pawan, my student, will discuss in his talk. But to do that, we had to change little. This also has inversion, by the way, the original model. But to calculate the invariant, we had to do a little bit of change. We had to just put a phase slightly. All this means is, this half is, the Moiré modulation hopping is just shifted in phase. Okay, nothing else is changing, but this helps us in our calculation. So then we immediately take Fouquier invariant, which is standard. You take the time reversal invariant momenta, and you calculate the parity operator eigenvalues, multiply that, and if that thing is -1, we know it's topological. If it is not, it's trivial. So what do we get? Here is the phase diagram. First, without flux, when J is even, J is the periodicity. When we have even sites, it turns out that when J is positive, it's always topological. G. G again is the strength of the interleg modulation part. Okay. It's always topological. When G is negative, it is never topological. And as you can see, doesn't depend on the periodicity that I'm choosing. When J is odd, however, then it's a slightly more intricate phase diagram. Again, negative G doesn't give us anything, but at positive G, there is a substantial region that is topological, but then beyond some point, it reverts back to being non-topological. That was without flux. Now with flux, we see exactly the same thing, no change. If you can compare these two, see, I'm changing slides and there is nothing changing, which is even J shows always positive G topological, and if it is odd J, there is a patch where things are topological and then it becomes non-topological. Okay? So the gist is that the take-home message is, I have my parent system which is purely non-topological, but Moiré alone induces topology. And the general message is, to do that in an arbitrary multiband structure, you have to take care of the symmetries, and that becomes a bit of a case-by-case basis. But the interesting thing is that flux doesn't play a role. So I showed you in interaction, the momentum separation through the flux was crucial. In the topology, this plays absolutely no role. It is entirely the Moiré modulation that plays the important role. Okay? Again, for further details, the bulk boundary correspondence is slightly non-trivial here because, again, no symmetries protect the edge modes. So those things and other aspects will be discussed by Pawan, the last talk of the conference on Wednesday. Okay. All right, 1 minute. Okay, just what next? I think there are a lot of things that can be done. Staying within this ladder model, now you can play a lot. For example, you can actually add just a sublattice in each leg, essentially put an SSH, and then you can mimic more of the sublattice degrees of freedom. So I can put layer by layer now and increase the complexity and take some of the attributes from twisted bilayer. So if you put that, then you can study that. You can also add valley. You just take two such ladders with opposite flux, and that essentially are the two valleys of your twisted bilayer graphene. And then you can also go and actually, so we're doing that, we have also gone into the 2D sector, but not yet with graphene. You just take two square lattices, and because I'm playing the momentum separation of the individual layers are important, you can play with each individual layer and take more than nearest neighbor hopping, and that will take care of the low energy sector from the gamma point to some other point in the Brunoise zone. So when you rotate them, either your Moiré will form around gamma or at finite momentum, and that can give you, and I can manipulate that by changing my hopping in each layer, and that can give me a nice study of a crossover, how that phase changes because of the introduction of the momentum separation. All right, so here is my summary. The take-home message is this ladder is a minimal model which incorporates momentum separation through flux and periodic modulation that can help me deconstruct many of the aspects of modern physics. When in the interacting part, momentum separation turns out to be crucial in generating unconventional phases such as ferromagnetism. In the topology sector, periodic modulation alone determines it, flux doesn't play any role. And finally, interactions in topology are affected by different ingredients. I would like to thank some of my collaborators who have been active in different parts of these studies. Firstly, Pawan, who is my PhD student about to graduate. Ranjit, who was earlier a postdoc with me and is now in Japan. Ijuan is a postdoc in Riken, and part of the work was done with Pawan Husur in Houston. And I'd like to acknowledge funding from erstwhile SERP. Thank you.
So size in the geometric application, you would use the multiple.
So J is 6, and that was done 144, so times 2, 288 plus 2.
And it's an infinite geometry.
It's open boundary condition.
And the magnetic units are
6, J equals 6. Because I have made the magnetic same with the interlink.
I was wondering if you didn't have the ladder physics, but just had a 1D and added next nearest neighbor, you could get to a 4-1B point.
Exactly.
Is that reproduce this, or is the flux? I mean, you constructed a model where you had flux and then you had periodicity, etc.
No, so within a ladder, if you put higher hopping, that will do something, but I want the momentum separation between the 2 degrees of freedom, which are coupling.
So
that is important, right? Because in TBG, the top layer and the bottom layer are getting separated. That's why that flux was there.
I have a curious question.
Yes, Vidisha.
So, do you think the momentum separation mechanism that you're talking about, can there be an analog in like bosonic systems like model excitons or like model ladder kind of picture, or is it fundamentally tied to fermionic?
No. It's the model is. I am studying fermions, but it can happen in anything. Yeah. Absolutely.
Okay. Are there any work that is already going on in that regard?
I'm not aware of that. Yeah. See, I'm not an expert in 1D physics per se. I'm coming from a very different direction. So maybe someone in 1D will have a better answer on the state of the art.
The masters.
Yes.
So I had a quick question about
Yes.
the topology. Why winding number is not a good topological invariant here?
No. The Foucault is, at the end of the day, winding number. It's a shortcut way to
I see. Okay.
calculate it.
I see.
Okay, let's thank Vidish for excellent talk.
Thank you.
Okay, our next.